I'm happy to present Ransom Stevens today. He is a really diverse character, and I'm happy to be meeting him today in person for the first time, although we've corresponded a bit over email. He was on the physics faculty at the University of Texas at Arlington. He was a collaborator on the team at Fermilab that discovered the top quark. He is National Science and Society Correspondent at Examiner.com. He's a noted public speaker. He's author of numerous technical and non-technical publications, including his novel The God Patent, which is the first novel to advance from online ebook status to print success. The God Patent includes a major character based on the protagonist of today's talk, Emmy Noether. I'm happy to present, and please welcome Ransom Stevens.
Thank you. All right, so how many of you have heard of Emmy Noether before, at least before reading the God, I Love You? See, I give this speech in the Valley, and I don't have to explain quite as much, right? So, as you know then, Emmy Noether was a turn-of-the-century mathematician who lived in Germany. It's amazing. I've converted this little area to my office already. So this is what I want to cover today. And I really appreciate you coming out. And I'd like to thank Robert for having me. So here's our agenda. This talk is a mix of science and history. The history is biographical of Emmy Noether's life. Emmy Noether led a very interesting life that was challenging, but she was a very happy person. So we will cover that. We will talk about Noether's theorem. I will explain the physics behind Noether's theorem and more history. We'll go back to history with Emmy's reality over there. And then we'll talk a little bit about two major problems in particle physics because they directly relate to Noether's theorem. First, the matter-antimatter asymmetry, and then second, the origin of mass problem, which translates into the search for the Higgs boson going on at Fermilab outside Chicago and at CERN, straddling the Swiss-French border. Then finally, we'll wrap up with just a few words about Emmy Noether, and then I'm going to sell you my book. We'll see. So first, Emmy Noether was born in 1982 in Erlangen, Germany. Her father was a math professor at the university there, at the University of Erlangen. In 1900, when she was 18, Emmy got a teacher's certificate. This was pretty standard fare for a brilliant young woman. The plan was that she was going to teach French and English and German to students, to girls, at girls' schools. But then she decided she wanted to be a mathematician. Now, this was kind of a weird development in 1900 Earth, but especially 1900 Germany, right? Because she did have this problem of being female. And so she couldn't register for classes at the university. She did have the advantage that she knew a lot of the math faculty since her father was a professor there. And so she was allowed to audit classes, right? We've all thought of this. I think every time when I was an undergraduate and took the check, from the financial aid office across the street to the cashier, that 3-hour thing where you stand in one line for an hour and a half, you get the check, you go stand in the other line for an hour and a half, you give them the check that, I could just take this check and I could sit in on those classes and learn the same stuff. She actually sort of did it. She did her bachelor's degree in mathematics without ever actually enrolling in a class or taking a test. But she did take the final exam. In Europe then, and still in many cases now, it's common to have one grand exam at the end of the program upon which all things are based. And she did very well on that exam and was granted a bachelor's degree without ever actually having to pay registration, though I don't know that they actually paid then. In 1904, she went ahead and applied for graduate school and ran into many of the same obstacles. But then, having performed so well on the grand exam of the undergraduate program, she was allowed to enter the university as a graduate student. And 3 years later, she obtained one of the first PhDs that was granted to a woman in Germany. Well, after that, what do you do, right? What do you do with a math degree when there's no software industry to go into? You want to do more math, so you do some pure math. So she set out for a faculty position in Germany, which was rather ridiculous at the time, of course, with that same handicap being a woman. She went to Göttingen, the University of Göttingen, which at the time was kind of the center of the mathematical universe. This was a place where all the heavyweights were working right around 1907. And remember, 1907 is 7 years after Planck discovered that something was funnier about light than was expected prior to that. So it was a very exciting time to be in mathematics and mathematical physics in particular. She took an unpaid position, and what that means basically, she was teaching some classes as a guest lecturer and studying with doing math, right? Cutting edge. Her parents died, and she got a small inheritance from her father, of course. Her brother got the lion's share of the inheritance by virtue of being a man. But she was able to survive at the university on a combination of her inheritance, her natural lack of interest in those things material. Well, I don't know if it was natural, but she certainly ended up with a lack of interest in things material by virtue at least of her inability to obtain them. She was also floated the occasional Deutschmark for covering for professors. They needed her there. They knew how good she was, and she needed some cash to stay. Then, in 1916, she formulated what would come to be known as Noether's theorem, which we're going to talk about in a minute. But as she struggled through producing lots of papers, which of course is the thing that professors are expected to do, even now. But she couldn't be a lead author on a publication. So she was a secondary author on many major publications, not the least of which came to be known as Noether's theorem. And then in 1919, it came to the faculty, a meeting of the faculty at the University of Göttingen, that they had this brilliant mathematician, and can we grant her a faculty position? It was 1919, which of course it was just after the armistice of World War I, and this is rather in the center of Germany. I always print this up so I can get the quote just so. In 1919, the History and Philosophy faculty in the Faculty Senate at the University of Göttingen said, "What will our soldiers think when they return to the university and find that they are required to learn at the feet of a woman?" It's unthinkable. But she did get, again, through the back door, what's called a Privatdozent position, which is somewhat below an instructorship in America, somewhat below an adjunct professor position, which means basically that she was kind of a TA, like a graduate student, but she wasn't a graduate student, of course, because she couldn't enroll there anyway if she hadn't already. Anyway, so you get the picture. But it was finally in 1922, she finally got her first academic income. So let us turn now to some of the science. And Noether's theorem is most succinctly put like this. For every symmetry, there is a corresponding conservation law. And this is how it works. Rather than develop the formalization and do a bunch of mathematics, pull up the screens and go forth on the whiteboard, I have built a machine. And this is how it works. We take the principle of least action, which I'll describe in a minute, and then a symmetry, and I will define what I mean by symmetry in another minute. We take those, we apply Noether's theorem, do a bunch of math, a couple of pages of, not even, but a page or so of algebra and calculus, and then bingo, out comes a law of nature. Okay? So prior to that, when Newton formulated his 3 laws of motion, what did he do? Well, he observed things like apples falling from trees and candles flickering and light through lenses and so forth to come up with them very empirically. But now, Emmy Noether provided some mathematical formalism from which, presented with a symmetry, a law of nature could be derived. So something very special is going on in there. Oh, and here's, of course, a copy of the original paper. I'm sure you've all read that already in the German and digested it. Good. So the first ingredient to developing the laws of nature is the principle of least action. Now, the principle of least action is a fascinating thing. And if it were attributable to one person, then I would have an accompanying talk about that one person, but it's not. It started in optics, the observation of the way that light rays travel by Fermat. And then Maupertuis, another one of the French mathematicians of the 1700s, formulated a more general theory, which was then elaborated by Euler, Lagrange, and then finally Hamilton put it together in the fashion that we know today. And basically, it is this. Stuff happens in such a way that a quantity defined as the action is a minimum. And the way I've always explained this, very hand-wavingly, is that the universe is lazy. And it will take the path from point A to point B, whether that is cooling a beer in the fridge, or the trajectory of a golf ball, or what have you, the trajectory of an electron through a circuit board. Nature is going to do it in the way that is easiest. And by easiest, mathematically, what I mean is that the action is minimized. Now, the action is defined up there to be the sum of the difference in kinetic energy and potential energy as things happen, all right? So if we take any system and add up the difference in kinetic and potential energy, the energy of motion and the energy available to do work, add that up over each incremental step of the system, and then postulate all possible steps, the actual process will be that which minimizes this quantity, the action. So here's an example, the golf ball flying across a golf course. We add up the action. If we follow the yellow line, which is kind of a weird trajectory it might have, then the action will be larger than the orange line, which is also clearly a non-physical trajectory, which is larger than the actual path which the golf ball takes. So that's how it works. That's the principle of least action, the first ingredient. The second ingredient is symmetry. Now, what I mean by symmetry is this. If we take a uniform sphere in the top left and rotate it, it looks the same. Doesn't matter which axis we rotate it about, but the sphere always looks like a sphere. If we go to the top right and look at a disk looks the same about rotations through about an axis that goes through its center. Okay, so those are simple continuous symmetries. An example of a discrete symmetry is what you have when you look in the mirror. I look the same, except that left and right are switched. Okay, so that's a discrete symmetry. So that's what I mean by symmetry. Now we have the principle of least action and symmetry. So let's plug them into Noether's theorem. Okay, so that's what we do. And here's what we're going to do. We're going to posit a symmetry. The first symmetry we're going to posit is very straightforward. And it is spatial translation. Now, if I look out upon the universe, it looks the same if I'm standing here as if I'm standing over here, okay, or even farther away. The universe is more or less isotropic. Another way of looking at this, and probably a more accurate way, is to say that if I do an experiment here, I will get the same result as if I do that experiment over there. Okay, that's spatial translation. Now that's symmetry. All I do is switch in my equations x prime to x, plug that in to the principle of least action, and use the mechanics of Noether's theorem, and lo and behold, we get Newton's first and second laws. Conservation of energy covers them both. Force equals mass times acceleration, and a body that is in uniform motion will continue in uniform motion until it is acted upon by a force, which is easier stated as a conservation law. the conservation of momentum. So what this tells us is that there is something very fundamental between the relationship of the geometry of space, just moving along one coordinate system in a straight line, and momentum. All right? The dynamics of the laws of motion are determined by the geometry of space, simple linear geometry. Okay, so let's do it again. Here's a better one. Let's say if I do an experiment now, I will get the same result as if I do that same experiment now. Time translations, very much like spatial translations, only now I'm saying, well, let's switch from t to t prime in the principle of least action. So we've applied those, we stick it in Noether's theorem, we turn our mathematical crank, and we get conservation of energy, which, for my money, is really very fundamental. The conservation of energy is something that we bump into pretty much all the time. No perpetual motion machines, no way to derive energy without doing something, right? Say, spilling oil all over the Gulf. It's not funny, but it might as well be. So this is the first law of thermodynamics, and we have tied it to the way that time evolves in the universe. There's something extremely poignant about that. I don't know what it is, but energy and time are intricately related through Noether's theorem. This very simple symmetry comes right out. So the story goes on. If we rotate a system, right, if I do an experiment with this orientation, I get the same results if I rotate the whole thing around and do the experiment like this. That gives us conservation of angular momentum, which is the reason that when you ride a bicycle, it's easier to stay vertical when you're moving than when you're at a stop. Also, it's why tops stay up. It's why tornadoes form. It's why the water goes down the sink the way it does with a vortex. So this is what I mean when I put in the title of this talk, The Fabric of Reality. It's not just that I like to say fabric of reality. Who doesn't like saying fabric of reality? Anyone? I didn't think so. Okay, there's one guy. There always is. Love that guy. So, Noether's theorem shows that the laws of nature result from symmetries, from geometries in the universe that we live in. The laws of motion are tied to spatial geometries. Work, heat, mass, all forms of energy are tied to the way that time evolves, to duration. And then what this starts to indicate is that space and time are a thing, that they have some properties that affect the stuff that fills them. That in fact, the laws of nature are not dictated by the stuff so much as by the background. The painting is dictated more by the canvas than the paint, if you will. Canvas being a fabric, see, tying that around. Yes, witty. So a vacuum is then, we start to get a hint that it's a complicated state. So now let's go back. Emmy Noether has just had her theorem published. It makes some waves, and these are her mentors and friends there at the University of Göttingen during her tenure there from 1908 to 1931. These are some big names in 20th century mathematics. Felix Klein from the Klein-Kaluza formulations. Hermann Minkowski did a tremendous amount of work in the geometry behind general relativity. David Hilbert did the mathematics for advanced quantum mechanics. Hermann Weyl did the geometry and math for a great deal of quantum mechanics. Major dudes. And Emmy was there with them the whole time. And in 1920, as quoted here, Hermann Weyl said, "To the faculty senate, I am ashamed to occupy such a preferred position beside Emmy, whom I know to be my superior." And among these guys, they were all close to her. Felix Klein was one of her closest friends. Well, I guess I can't really say that. The biography of Emmy is sparse. So, it's 1931, 1932, Germany. Emmy Noether is Jewish. She's an intellectual. You know, they always come after the intellectuals first. You notice that? It doesn't matter. The communists came after this, Stalin went after the intellectuals, the Taliban went after the intellectuals, some of the Republicans come after the intellectuals. They always come after the intellectuals first. And she was also a liberal pacifist. She really wasn't on board with World War I. So what happens? Well, you know what happens. So this bozo was not Emmy's friend. And she was one of the first 6 professors in Germany to be fired. Now her brother, who I haven't mentioned, was also a math professor. Her brother took their father's position at the University of Erlangen, and when in 1931, when the writing on the wall was becoming clear, it was much clearer for intellectuals than it was, or for academics than it was for people in business. But they had to leave. They couldn't make a living. It was unpleasant. Her brother went to Siberia, went to a university in Vladivostok, which eventually became a pretty big university, but there was a hiccup there. And Emmy didn't want to go there because it wasn't where all the math was going, where all the math was going on. And there is one line of thought that permeates Emmy's existence, and that is a deep passion for doing mathematics. It's simply what she wanted to do. She never got notoriety. While most of you have heard of her, you also know that very few people out there have. But they've all heard of Einstein. So that's who she turned to in 1933 for help. She wanted to go to the United States. And Albert Einstein convinced the Rockefeller Foundation to match the Emergency Committee to aid displaced German scholars, and got this woman, who has set the stage for formulation of the laws of nature from fundamental symmetry, got her a 1-year gig at Bryn Mawr. And for the first time in her life, she actually had an official faculty position, a 1-year position. Now, a little bit of background on Emmy's relationship with Einstein. She did a lot of the mathematics, the tensor mathematics, the multidimensional matrix formulations that are needed to describe warp spacetimes. She set up a great deal of that mathematics that he ended up using. So they knew each other, and Einstein was her mentee. A year after that, when her position ended, she had to once again scramble to have it extended. All right, it's kind of weird, right? Perhaps the greatest mathematician alive at that time, and she can't get a job at Bryn Mawr, while her mentee is, of course, leading the Institute for Advanced Study at Princeton. Such as it was. Thing is, I don't think Emmy really cared that much as long as she could find a place to do math. So let's carry on, go back to the science. Now, the interesting thing in physics is when the theory falls apart. What happens when it doesn't work? That's what experimentalists always want. Proving a theory works is boring. But if you can take something that is on the pedestal and knock it off, that is where careers are made. So we look at this and say, well, what happens when we think we have a symmetry, and then we plug it in, principle of least action, apply the symmetry, turn the mathematical crank through Noether's theorem, and we get a result. Something that ought to be a law of nature if that symmetry is truly symmetric. So we apply that, and that. Well, the principle of least action is built on a pretty strong foundation. Noether's theorem is simply mathematics, right? So you can prove it. It's mathematics. Just prove it. There's nothing really to question there. So what you would question is the symmetry at the other end, your hypothesis. So what do? Well, of course, I have another box, this one considerably more expensive than the mathematics, the experimental green box. So what do? You do some experiments and you find out, do the predictions, or is that law of nature, does it hold up to experimental scrutiny? If not, then it's what you call a broken symmetry. And broken symmetries then beg a lot of questions. What is their ultimate impact on the nature of matter? So, here are some interesting symmetries. They look at first glance. Some of them look at first glance as if they ought to obviously hold. For example, parity. Parity is this left-right switch. When you look in a mirror, if I do, remember when we did time translation, the issue was if I do an experiment here, I get the same result as if I do it over here, right? Time translation. Now, parity, this switching of left-right, means if I do an experiment here, do I get the same result as if I do that experiment and rather than watch the experiment rather than take the data from the actual experiment, if I take the data from the mirror image, do I get the same results? Seems like you probably would, doesn't it? Well, you almost always do. So it's kind of obvious symmetry. But you plug it in and something strange happens. Now here's another symmetry, time reversal. If instead of going forward in time, if I go backward, will things look the same? Well, it really doesn't seem like it, because my hair's not getting any less gray, right? Time has an arrow. So this looks to me like a completely obviously broken symmetry. But if you look at the laws of nature, you know, the trajectory of a particle, the evolution of simple systems, not big statistical systems, but systems where you can track every piece. The equations are symmetric under time translation. So at the fundamental level, there's this problem that time translation looks mathematically like it ought to be a symmetry, though it clearly violates something. In fact, it violates the third law of thermodynamics. Entropy increases. So there's something funny there. Now here's another one that's somewhat more esoteric that we need to string all this together, and that's called charge conjugation. Now what charge conjugation is that we switch all of the charges of matter the opposite way. So for example, we take an electron, turn it into a positron. We make it from negative to positive. We just switch the charges of everything. A proton becomes an antiproton. Now charge conjugation amounts to switching matter and antimatter. Now since antimatter is defined to be the equal of matter except for this change, then in a universe full of antimatter we would certainly expect the laws of nature to be the same. Everything would look the same, it'd just have flipped charges. Instead of having electrons flowing through motherboards, you'd have positrons. Big deal. Okay? But there's something funny there too, right? Because this is an annoying problem, is that in every case where matter is created from energy, there are always equal amounts of matter and antimatter. So how come this universe has almost all matter and almost no antimatter? There's a huge broken symmetry. So one of the experiments that's been going, well, various experiments that have been carried out since the mid-60s have been trying to figure out where's this broken symmetry. So let's have a quick look at that. First, we switch the direction of time, and we do the left-right switch, and we switch all these charges. We apply all three of these apparent symmetries at once, and lo and behold, the product of them all seems to hold. It seems to hold. Okay? It holds in every case. But if we reduce that, if we remove the switching of forward and past, if we remove the time translation symmetry, then, and we apply just this left-right, the parity, and the matter-antimatter switching of charge, then there's a broken symmetry. There are just a tiny handful of processes involving these esoteric particles, kaons and B mesons, things that we just don't bump into every day, and there's this little itty-bitty asymmetry there where there's a tiny, tiny bit more matter than there is antimatter. That gives us two things. First, it gives us a hint as to why there's more matter than antimatter in the universe, but more interesting than that, well, I don't know, but equally interesting to that is that if CP, if the product of C and P is broken, but the product of CP and T is not broken, then that means that somewhere along the line that time reversal is broken too. So we can all breathe a sigh of relief because the third law of thermodynamics is then allowed to continue because there is a broken symmetry. Don't know what it is, trying to figure it out. So finally, the Standard Model has a problem. The Standard Model is this great big theory which is built on way too many experimental details. It involves nature at its most fundamental level. All of the matter that we're aware of, that we can easily observe, is made up of these things, quarks and leptons, and force fields that are given there on the side, photons, gluons, Z's, W's, and I drew in the big G for graviton. We don't need to know what any of those are to realize that this Standard Model of physics, it'd be perfectly happy if none of these things had any mass at all. But once again, we have a great deal of empirical evidence that we have mass. And in many cases, our mass is increasing as we eat more. There's mass. Where did it come from? How did it happen? In fact, if we do a rotation among all these particles, and just switch their names and leave the masses out, none of the laws of physics change. Okay? There's a problem. This is the origin of mass problem. And this guy here, Peter Higgs, at St. Andrews University, I think, maybe Edinburgh, he's a Scotsman. He formulated a theory about, and to say he formulated the theory is really giving him more credit than he deserves, but there is a lot of theory behind broken symmetries. And he used that to hypothesize a particle which appears when a symmetry is broken in a certain way, and he called it the Higgs boson. When I discovered a particle that decayed very quickly, I called it the R, because I thought it'd be too obvious if I called it the S, because my last name is Stevens. I thought I could get it by with the R, the ransom, but everyone knew. So this is what you do. Anybody here ever solved a differential equation? Yeah, so, you know, differential equations, what a pain in the ass. There's really, for an interesting differential equation, there is no simple pedestrian way. We start here, we try, you know, we do go through these steps to get the solution. They just don't work that way. There's a few that do, but they don't. Those ones aren't on the final, right? So what you do is you learn a lot. And what it looks like when you're a freshman and you have a TA who solves the problem on the whiteboard, it looks like she's pulling something out of her hat. It's like, I'll never think of that in a test. There's no way I'm just going to come up with that. But later, as you become a junior and senior, you realize that the building up of experience gives you an edge. And what that edge is you try things that worked before. And that's how you solve differential equations. Well, that's how you do most of mathematics and physics, is you need to just start trying stuff. It's like debugging problems with Microsoft code, right? It's not working, what do you do? Well, just go to options, go to the next thing. It's going to work eventually, reboot a couple of times, get Star Office. So here, the thing is, magnetism is a similar case. In a magnet is manifestly asymmetric, right? It's got a north pole, a south pole, but the equations that describe magnetism are radially symmetric. The equations have spherical symmetry. The solutions do not. They like to have north and south poles. They're dipoles. They like to be quadrupoles. They don't have radial symmetry. So that's similar to what's going on in the Standard Model. So what we do is we try the same thing. So with another interesting thing with magnets, which is directly related, is that if you take a bar magnet and you heat it up, there is a well-defined temperature called the Curie point where it loses its magnetism, where the equations that describe that magnetic field go from being manifestly asymmetric to being bing at one temperature, they suddenly become radially symmetric. Starts to sound a lot like what might have happened at the Big Bang. A very hot universe cools. And as it cools, something happens. So this is what happens. Particles obtain their masses through interaction with something that pervades, that permeates the vacuum. The vacuum really is something special. And it's got this background, the canvas of this painting might be the Higgs field. That heavy particles are constantly interacting, that the Higgs is slowing them down like a viscous fluid, whereas massless particles don't interact with the Higgs. They go zipping right through. Photons, light is massless. So where the iron filings line up with the magnetic field, the particles line up with the Higgs field. The top is the heaviest one on there, 171 times the mass of a proton, and it lines up with that Higgs really sharp. It's got a very, very strong coupling. So that's the idea of how the Higgs works. So now we turn to the straw experiment. This is very high tech. Who wants a straw? Who wants to carry on this experiment with me? Some of these symmetries have been broken before. Just fix your straw and go with it. It's an advantage to giving this in the, oh my, there's no end of straws over there. Let's not. So, this is the idea, okay? During the Big Bang, at the beginning of time, the beginning of space, the beginning of space-time, the universe was so hot. Thank you. See, Carson goes off the air and no one knows the line. How hot was it? Yes, it was so hot that the energies of these particles were just way, way bigger than their rest energy, than their mass. So if we look at Einstein's famous equation, E equals mc squared, and then write it down the way it's actually used by physicists, which is to say it's the rest mass, m0, times the speed of light squared, plus the energy of motion, in this case, the thermodynamic energy. That thermodynamic energy was so much larger than the rest energy that it was effectively massless, that these particles were massless, okay, when it was hot. So then the universe cooled. The universe cools. We press down on the straw, and as it cools more and more, the straw bends. It picks a direction and bends. It no longer has that typical spherical or cylindrical symmetry that we look for in a straw. It's a broken symmetry. And when that symmetry breaks, the particles begin to interact with the Higgs and obtain mass. The Higgs then becomes prominent at those temperatures and below. So you look at your straw and you say, but you know, if it didn't have this quirky little thing in it, then maybe if I pressed it just right with all perfect symmetry, then it'd collapse on itself, like that. Kind of like flipping a coin and having it land on its side. You've probably managed to do it, but I bet you couldn't right now. Something happens. Now, whether the universe was symmetric before it cooled, or whether there was an underlying asymmetry that caused this symmetry to be broken in a given way, just like the straw chooses a direction when I push down on it, I don't know. It doesn't really matter. The particles have mass. So this is then the fabric of reality with the Higgs boson. So the geometry of space-time dictates the laws of nature. Noether's theorem gives us that. And the space-time vacuum is saturated with this Higgs field. So if we want to detect this Higgs field, well, how do you detect the canvas on a painting? You're looking at the painting, right? How do you do it? Well, you have to bring the canvas to light. You got to move some paint off. You have to do something. And here, we have to inject energy into the system. The current state of our space-time interval, any random spot, this spot of space-time right here in my hand, is too cool for there to be any Higgs. So we have to inject energy in to get one to pop out. So the idea is basically like this. If we think of the Higgs field as a pool of water, then a wave in that pool is a Higgs particle. We have to give them energy. So yes, there's the experiment, the very expensive green box of experiment. Is this true or false? It's a broken symmetry. We have a concrete prediction. Do an experiment. So that's what these experiments are doing at Fermilab and at CERN. The Tevatron at Fermilab, which is in Batavia, Illinois, there are two experiments, the D0 experiment and the CDF experiment. These are great big things, 4 stories high, and I think D0 ended up costing, I want to say, $200 million just for the detector, not including the accelerator. And then there's, at CERN, the ATLAS experiment. There's 2 major experiments there that we'll be looking for the Higgs. The ATLAS experiment, which is an acronym. ATLAS stands for A, toroidal LHC apparatus. ATLAS. Yeah, real creative, these guys. And there's another one, the CMS, which is compact muon solenoid. So there are these 2 experiments going on, and they are literally dumping energy into the vacuum and try and look for certain signatures that will tell them if there is a Higgs. Now, interesting thing. There are various constraints that you can put from other measurements where evidence of the Higgs must lie, even though it's not clear evidence, that limits the processes, so that if the Higgs is not found at either Fermilab or CERN, then it's out of play. That mechanism doesn't work. And if that happens, well, then things get even more interesting, right? The the theorist, I bet Peter Higgs would really like for the Higgs to be detected in his lifetime. That would be tidy and nice. But the experimentalists across the hall from him, no Higgs. They want Technicolor. Technicolor would be cool because it's another layer off the onion. We had that little chart of quarks and leptons. Technicolor would say that there's another layer, that quarks and leptons can be broken up into smaller things. That's always kind of, the first knee-jerk response, since we've all seen the way things go, right? You have atoms, then atoms are made up of stuff, then protons are made up of stuff. It only seems natural there's another layer. And there's other approaches. One of the interesting ones is that there could be extra dimensions, that there could be something happening in an extra dimension that leaks into our reality and gives these particles mass. Finally, Emmy Noether. All these laws, all these theories that involve symmetry are built on top of Noether's theorem. In fact, superstrings, the standard model of physics, these are all called gauge theories. And gauge theories are built immediately on Noether's theorem. Every law, everything that they predict is ultimately predicted by something that you can get using Noether's theorem. So that's the reason that I think that Emmy Noether made arguably the most important discovery of humanity. This relationship between the fabric of reality and the way reality is, how it works, the effect of the canvas on the painting. So anyway, she moved to Bryn Mawr, where she got a 1-year position, which she got generously extended for a year. She had a reputation for being a very challenging teacher. She was the kind of teacher who would put a really hard problem on the board and then ask you how to do it by name. And this can be very painful, right? But she was one of those teachers that we've all had that at first we hated. And then as time went on, we realized, no, wow, she's really cluing me into something. There's something special here. And then you really learned. So she had a squad of students that followed her around in Germany that ended up being called Noether's Boys. Of course, she didn't have any female students because there weren't any. And then she went to Bryn Mawr, where it was an all-female school. And it was the first time she'd had female colleagues, and she was very, very happy there. But during her second year as an instructor at Bryn Mawr, she didn't feel well, and she didn't tell anybody about it. She went to the doctor, and the next day she missed her lecture, and no one was like, Emmy Noether misses a lecture. It's never been done before in history, but she was dead. So she went to the doctor. She had an ovarian cyst. It was removed. It was 1935. Things didn't go too well, and she died 2 days later. But, and that's why I set this here, that from my impression of researching her is that this complete lack of notoriety that she had through her life and after her life, I don't think it mattered to her. I think she was very happy. I think she really enjoyed doing mathematics. She was well known for doing things like walking into walls and stuff, thinking about math and forgetting things except her students and her classes. So those are good reasons to remember Emmy Noether, and she's not completely without notoriety. You can see a picture up here, which is on a library at a girls' school in her hometown of Erlangen. They ought to trim the bushes out of the way, but it's a plaque in her honor. And she is honored in various spots, including Bryn Mawr and now at Google. So here's a list of things she did, and if any of you are real pure mathematicians, then you might be writhing in your seat that I didn't even mention her most important contributions, because I don't really understand them, so I wasn't going to mention them, but I figured some of you might have known them. But she did a tremendous amount of work in non-commutative algebras. You remember that? That's where the law of the distributive property doesn't work. A times B is not equal to B times A. And group theory, which all seems to have to do with donuts, and hypercomplex numbers, and rings, and the theory of ideals in rings is known to be one of her greatest contributions. But as a physicist and as an existence in this universe, for my money, Noether's theorem was really huge for all of us. So, how does that fit in? Well, Robert told you at the beginning that this brilliant novel that was composed by someone in the room involves a character that is based very loosely on Emmy Noether. My character is named Emmy Noether, and I propose this, that had Emmy Noether grown up in 1980s Los Angeles, she would have been quite like my character, Emmy Noether. But Emmy Noether grew up in the Kaiser's Germany. It's the only reason they were different. Truth is, when I wrote this book, Emmy Noether was sort of a hero of mine just by being a physicist. And so in the first chapter where she appears, it's her giving a lecture teaching her students at Cal Noether's theorem. But she doesn't call it that. She doesn't say what it is. But when I wrote the book, I hadn't done any research on her at all. I did all the research afterwards. So by very loosely, I mean very loosely based. So this is my book. I have a few copies if you want it. You're welcome to buy it on Amazon. I actually get a really nice royalty if you get it there. It is available, of course, in Kindle and so forth. And what I want you to do, if you can just take a couple more minutes, is I have some evaluation forms. I'd really appreciate it if you could crank them out real quick. Let me hand them to you now. Would that be okay? All right, thanks. I'll take questions. Yes, I'll happily take questions. Shoot.
So while he's working out the story with the evaluation forms, I'll ask the first question. This question is actually inspired by a piece of email I got from someone who, I don't know whether this person was able to attend the talk or not, but someone sent me email and said, just a question for Ransom Stevens. And I won't tell you initially what the question was, because
that'll make it easier to answer.
Well, I want you to answer a different question, and
okay.
That's why. This is a question begged by the question I was asked to proxy to you in email. So Noether's theorem that you told us about starts you with a symmetry and gives you a conservation law. And the question begged by the question I got in email is it the case then that for every conservation law there is a symmetry?
Yes. For every conservation law there is a symmetry.
So the question I got in email is, given conservation of information in quantum mechanics, what is the corresponding symmetry?
I don't know. It's a very interesting question. I don't know.
I gather the person who asked didn't know either.
Yes. But I bet this person didn't know. But information is no, I don't know the answer, but it's certainly worth trying to dig up. I know some people that I can ask. Sorry.
So first, thanks for the talk. If I only understood half of what you said, would have been even better. Question is, I think I read this morning or maybe yesterday something about in the LHC there was this experiment that the results seem to indicate there might be 5 different mass Higgs bosons or something.
Yeah, one of the things about the Higgs is that it takes more than one, and there could be a lot of them. Okay, the Higgs gets complicated very quickly. Yes, there's likely, if there is a Higgs, there's probably 5 is a good number. 5 is, I think, the minimal number, 1 for each generation. And they couple differently, and they'll have different properties. Some of them might be charged. The minimal Higgs boson is a neutral scalar. It's a neutral spinless object.
I'm curious about the title. Why the God patent?
Oh, the God patent. The reason that my book is titled The God Patent, I did not pay him to ask this question. The reason that this book is titled The God Patent is this. It's the story of a laid-off engineer trying to rebuild his life after making a great deal of stupid decisions. Okay, so he was, in 1999, he was working for a company in North Dallas that did fiber optics, and it just started doing fiber optics, right? It was 1999. It was a very exciting time to be in high tech. And as you probably did when you were first hired here at Google, in his orientation package there was a memo that said if you submit a patent you will get a bonus, and if that patent is then granted you will get another bonus. And so Ryan McNear and his buddy Foster Reed, 2 of the characters in this book, sitting there looking at it, and Ryan says, you know, we got a couple of hours, and the patent attorneys for this company, they don't know anything about the kind of high tech we're doing. Let's just crank some of these out. We can get a boat. So they did. And what Ryan thought of was to submit a patent, which ultimately was patenting the soul and calling it a software algorithm, that it was a neural network that begot other neural networks in a semi-biblical way. But it was artificial intelligence dressed up in enough engineering ease that it could get by the patent examiners for that company. He didn't expect it to be granted, but it was. His friend Foster patented creation and called it, of course, a power source, a generator, a power generator. Now, so this is kind of funny, right, that you submit some crazy thing, you dress it up in enough engineering jargon, and it actually gets granted as a patent. I'm sure no one in this room has ever done that. But I know a guy who works at a company that makes semi-processors over here somewhere, or I guess over there somewhere, and he has the patent for drilling a hole in fiberglass. Not vertically, right? That'd be a via in FR4, right? But he's drilling it horizontally. Patented that. Called it an optical coupling channel and dressed it up in a great deal, you know, lots of flow diagrams and stuff, but boils it down, horizontal hole in the fiberglass. You're going to have to pay Intel royalties for that bad boy. Next question? Any question at all?
Okay, go ahead. Okay. So in the abstract, you said that Noether's theorem was violated, and you would give examples. But my understanding is that it only applies to continuous symmetries. So it wouldn't apply to your discrete.
No, it does. It applies to discrete symmetries. In fact, some slides that I actually left out because we didn't have time, is that the first one you learn, the first application of Noether's theorem that you do in a textbook in quantum physics is the conservation of charge. And that's actually a discrete symmetry. You multiply a phase to the wave equation and then go through Schrödinger's equation and require that nothing change, right? Because just altering a phase can't change anything. And charge conservation comes right out.
Yeah, it comes out of the global phase.
Yeah.
I actually wanted to comment on the popularity of Noether and the relative popularity among mathematicians and physicists. Because in algebra, for example, it is completely impossible to publish a paper without mentioning Noetherian ring, whereas in physics it is still possible to publish a paper
It is possible.
that will not mention Noether's theorem.
Right. Thank you. In defense of mathematics. You don't get that at the Atlas Cafe in San Francisco.
This is a really dumb question, I'm sure, but you said you talked about experiments and their results being invariant. I mean, I wonder what you meant by an invariant experiment over space, say, because if I take a measurement on my GPS and then do it over there, the result's different, right? So that experiment's not invariant.
Yeah, you didn't move.
I have to move the whole system. Okay, got it.
Yeah. The whole experiment, the whole system you're doing needs to move, right? Or you're changing the symmetry of the system. But for GPS, if you measure GPS, I think a way you could gauge that is that you throw out you measure it twice, right? You measure it with how far you're moving away with a yardstick, so you actually measure, and then you put in the right x prime. And that will change your result, your measured result, and your predicted result, and you get the same. Okay? So you can't sweep anything under the rug, except the isotropy of space. That is what we're testing. Is that it? We have one more? Another?
It's about the Higgs boson. So I heard that the way that the Higgs boson would explain all the masses of the fundamental particles is that different particles would couple to the Higgs field with different strength. And so if we indeed find the Higgs boson, then aren't we just exchanging all these mass values with a set of coupling constants to explain? I mean, it's like we're exchanging a set of unknowns with another set of unknowns. So what's the advance in that case? Right.
This is a good point, and frequently experiments feel like this, right? It's the issue of we answer one question and it brings up more and more. So the answer is that if we discover the Higgs boson, that hopefully we'll make measurements that will dictate how it couples to different particles, but they'll all be tied back to the way that the symmetry breaks, or to something fundamental. Yeah, if we have a different coupling for every particle that exists that has mass, then we haven't bought ourselves anything. We're just, in fact, we've lost, because we got more particles and the same number of things we have to measure, so that doesn't get us farther down the road. But the thinking is that understanding the mechanism will get us farther.
Before we let you close, I just want to check and see if there are any questions from the remote sites. Okay, looks like there are not. Are there any more questions here? Please help me thank Dr. Stevens.
Thank you very much.